Our next speaker is Nick Lamke. He's a hydrologist with Intera, and he specializes in model development, remote sensing aquifer testing, data management. Let's welcome to the stage Nick.
Sorry, I'm just trying to play with the remote real quick. Is there a laser pointer on this? Oh, got it. Sweet. Okay, we're ready to roll. Okay. Yeah, I'm Nick Lamke. I work for Intera. I'm a hydrogeologist. I had the opportunity to work with Central Texas GCD to take a look at the drawdown impacts of private wells in a vulnerable section of the Trinity Aquifer in northeast Burnett County. Kind of a general outline of what I'm going to talk about. We looked at kind of the overall objective of the study was to demonstrate how the future planned growth could affect groundwater availability in the northeastern Burnett County. And the primary tool we used to do this was groundwater modeling with a program called TTIM. And kind of the sequence of events that led up to the groundwater model is we characterized available drawdown and aquifer properties, then created the simple groundwater model to run some exploratory simulations. And then I ran a sensitivity analysis, and we also tested the effects of recharge. So a little bit about the background, where are we at, and what kind of geology are we working with. We're in Central Texas, so the Burnett County is outlined in red here. In blue is the outcrop and subcrop parts of the Trinity Aquifer in Texas. The geology we're working with is the Trinity group of sediments right here, and you'll hear me talk about the Glenrose formation over here, and then we have the Travis Feet group of sediments, and I'll be talking about the Hensel, Cow Creek, and the Hostin units there, so you'll hear me mention those. So that's the sediments that are of importance in this area. So kind of a little bit more about the background, kind of diving into the details. So really the study area is up here in this northeast section. In this part of the aquifer, the available drawdown is pretty low, and the transmissivity is also pretty low. And they're also experiencing a pretty big demand on growth, population-wise. And they depend a lot on private wells. So anytime there's a new development going in, houses need a private well to get their water. So that kind of raises some concerns. When you have low available drawdown, low transmissivity, and a lot of growth, you're going to see more wells going in, which is going to cause more drawdown. So kind of the idea behind the study was to take a look at what that can look like, given the aquifer properties here. So just kind of to reiterate, the intent of the modeling was to demonstrate how future planned growth could impact groundwater availability. So I mentioned available drawdown, so that's an important metric. So why is it important? It's available drawdown is the difference between the static water level and some defined critical limit. So a critical limit could be a lot of things. We have some examples up here. Pump setting can be defined as a critical limit. So if that's your critical limit, the amount of water, so you'll calculate the amount of water sitting on top of your pump, and as you approach zero, it's going to tell you when you're going to have to take some kind of action. So if you get close to zero water above your pump, you're going to either have to lower your pump or drill your well deeper or drill a whole new well. So for the groundwater availability studies that led up to the modeling, the metric that they were looking at was the bottom of the aquifer. Sorry. When that is your critical limit, and you approach zero, there's no more water in the aquifer. So, and that looks different if you break your aquifer up into formations, so that amount of water sitting in the water column is going to be different for different formations. But when you approach zero on the bottom of the aquifer for available drawdown, there's no more water. You can't get any more water out of that aquifer. It's done. So it's a useful metric for determining when things are going to be really bad. So here's a summary of what the available drawdowns were in 2023 for Burnett County here. So we have broken it down by up dip, middle section, and down dip, and I'm showing the lowest unit, the Hostin, in this map right here. So you can see in the up dip sections, we're already less than 50 feet of available drawdown for all the water-bearing units in this area. And as you go down dip, there's a little bit more water, but 3 of these units are already less than 100 feet of available drawdown. And there's a maximum of about 300 feet of available drawdown in the deepest parts of this aquifer. So there's not a lot of water, and any additional stress, especially in these portions of the aquifer, could have significant impacts on that aquifer in terms of completely dewatering it. The other thing that's important to consider with aquifer vulnerability is the transmissivity. So we calculated some transmissivities from aquifer test data we gathered in a couple of different existing developments. And we got an overall mean of about 78 feet squared per day and a median of 55 feet squared per day. So some notes about the data that we received. There's a wide range of transmissivities, even within a development. It can be between less than 10 feet squared per day to over 150 feet squared per day. Some of that may be due to the fact that a lot of the wells aren't fully penetrating, which is kind of skew the results of an aquifer test and give you a higher transmissivity or lower transmissivity. But we needed to pick a couple of benchmark numbers to run simulations in the models. We went with leaning on the median because it's less influenced by extreme values, but we ended up running both the mean and the median in this case. But the main point is that generally speaking, the transmissivity is pretty low. So in general, in the Trinity Aquifer in Burnett County, the range can be all the way up to 3,000. So in particular, this area is quite low in transmissivity. So it's not a very productive part of the aquifer. So that kind of led into the groundwater modeling. So we know that it's stress. We know that additional pumping is going to cause drawdown. So let's look at so the point was to look at what that looks like with the groundwater model. So we use TTEM. It's a Python package for modeling transient multi-layer flow using analytical elements. In TTEM, it's similar to the TICE solution where you're assuming the aquifer is homogeneous and the properties are the same in areal extent. And you can it's different from TICE in that you can add some complexity. So you can stack up layers in the model and get some vertical leakage, and you can also add in elements like wells, rivers, and impermeable boundaries. So you get a bit of complexity. They're simple and fast to set up, and they're really good at calculating drawdown, which is exactly what we wanted to do in this study. So the main output from this model is going to be hydraulic head and drawdown. So that's the code we used to set up the framework for the model. We didn't know where developments were going to be, or how big they were going to be, or how many houses they're going to be on there. So it's an exploratory model, so we needed to come up with a framework for how big a development could be, how many wells could be on a development. So we kind of took some inspiration from the public land survey system. We made the biggest development size, 640 acres, and we used 4 other sizes for developments, getting smaller. And we had 5 different property sizes. So property size is really just just the lots. So if you were to break that development into different lots, and each lot had a well on it, how many wells would that be? So that's kind of the framework for where wells were at. So for example, I'm sure that was kind of confusing coming out of my mouth, but the 640 acre development size and a 2 acre lot size, that would be 320 wells inside that 640 acre development. Likewise, if you had a 40 acre development size and a 10 acre lot size, you would have 4 wells on that development. So that's kind of how the model was set up and what determined the number of scenarios that we ran. So there's 20 total scenarios for a single development situation. And here's kind of an example of what that well field would look like. with a 640-acre development and a 2-acre property size. So there's 320 wells evenly spaced in between that property, that development. So the aquifer parameters we ran into the model were the mean and median transmissivity for the Travis Peak, and then we had an average storativity. We used a pump rate that's normally used for private domestic wells in state planning. We ran the model for 30 years and looked at drawdown at 30 years. So every plot that I show that has drawdown on it is going to be the drawdown at the 30-year mark. And we calculated the mean and max drawdown for each scenario. So when I plot this up, you get a pretty intuitive trend. So what we have is some sensitivity to transmissivity, as you'd expect, and we have on the x-axis here we have the development size, and on the y-axis we have the drawdown values. So as development size increase, and in color-coded here, I have the lot sizes. So if you remember, a smaller lot size means more wells on each development. So as you'd expect, with a smaller lot size and a bigger development size, you get more drawdown, and vice versa. So smaller lot size, bigger development size, you get overall less average drawdown. So this was just kind of to set up the model, make sure everything was working. It's fairly intuitive, so we know that we're going to get more drawdown if we put in wells. So what we wanted to do is add a little bit more complexity. And I have some plots of what that drawdown looks like for the single development in aerial view. So you can kind of already see that if you stick 320 wells in a 1 by 1 mile grid and pump it for 30 years, you're going to get a lot of drawdown. I think you can't see that number on there, but in the middle, it's like 400 feet of drawdown. And about 4 miles out is going to be 70 feet of drawdown. And if you remember from our plot, a lot of those units are going to be nearly gone at less than 50 feet of drawdown. So it kind of gives you a feel for how many wells are going to be a problem and what kind of density is not going to work out. And this is just an example of what it would look like with less wells for the same development size. So quite a bit less drawdown. I think this is 20 feet of drawdown over here and 20 feet of drawdown right there. So the next thing we did was wanted to do the sensitivity analysis. So we needed to add in a little bit more complexity here. So I have this Rubik's Cube looking setup. So I needed to set up like a grid system to define where developments could be so that I could randomize their locations and randomize how many wells were in each location. So kind of the biggest unit of that property size is going to be that 640-acre development size. So there's 9 of those in a grid, and if you break that grid into the smallest units, that's kind of what it looks like. So this is the fictitious grid that we created to have a system for locating developments and wells. So here's kind of an example of what that looks like and kind of how this randomization works. So I randomly selected a development size in the center development. So the center development always needed 1 well, or always needed 1 development active. Then I randomly assigned 1 or 8 of these surrounding developments, surrounding grids in this development, a development. So there could be 9 total active developments in the grid, or just 2. So that's kind of the 2 extremes. It could be anything in between that as well when it was randomized. And on top of randomizing the size of the development in each of these squares, randomized the number of wells or the lot size in each of these squares. And then calculated the mean and max drawdown and ran 500 iterations of that. So in this example, there's 829 total wells, and in this one, there's 10. So if we look at the lot size breakdown of that, that's what the well field looks like, and that's what was input into the model. So there were 500 iterations of grid systems that looked like this with different combinations of wells in different locations. So when we look at the results for that, so I just threw up another example of the spatial distribution of drawdown. Obviously, if you put in 1,000 wells in a 800 wells in a 3-mile square grid, you're going to get a lot of drawdown. So I can't see that number from here, but there's over 500 feet of drawdown, I think, in the middle of this. So obviously, that's not going to work for this aquifer, but it gives you an idea of when we plot these up, it gives you an idea of what's going to happen when you start clustering wells in different ways. So here's the results of the sensitivity analysis. So there's two main things I wanted to point out. So on the x-axis here, we have the number of wells. And when we look at it this way, we see, and on the y-axis, we have drawdown again. When we look at it this way, we can see, obviously as you increase the number of wells, you get more and more drawdown. But also, you get to see the spread in here. So for a situation where you have 200 wells, there's multiple different configurations that'll get you 200 wells, but there's different kinds of drawdown you'll get. So depending on how you organize that well, I like this plot because it shows you that well spacing matters a lot. And as hydrologists, we all know that that's a critical component in designing a well field, but in an aquifer with not much available drawdown to work with, 20 feet could save you, and if you needed 100 wells, there might be a way for you to organize it so you could get the water you need without drawing down too much water. Also, I wanted to point out that at 100 feet here of drawdown, the Cow Creek would mostly be out of water. So we're looking at a little less than 200 feet, 200 wells here, and in 30 years, one of these units is going to be almost completely dry. Likewise, the Hensel down here at 75 feet, maybe like 150 wells there, and we're looking at large swaths of that formation just being completely dry in 30 years. So it's a good way to kind of get a feel for how many wells in an area are going to be a problem in 30 years. So the last thing we looked at was the effects of recharge. In this area, the Glen Rose overlies all of the Travis Peak in most areas. So kind of the idea of incorporating recharge into the model was that any aerial recharge that was occurring or had to pass through the Glen Rose formation to get into the Travis Peak. So we could simulate it as a vertical leakage from the Glen Rose formation. And to do that, we needed to get some properties for the Glen Rose. We ended up with two transmissivity values, 72 and 5 feet squared per day. We didn't really have any idea what the KV would be. There wasn't enough data to calculate one, so we grabbed some textbook values and decided to test the sensitivity with a couple of different orders of magnitude there. And we just ran the same simulation for the Travis Peak as I did before. And a couple notes about the transmissivity for the Glen Rose. There was a really high value measured in the area at one of the developments. So we decided to include it because it was there. But what we typically most often see is this lower number at 5 feet squared per day. So that's kind of what we would expect it to be. But we decided to test both just to see what a high and a low T situation would look like. So there's a lot going on this graph. I have 20 different scenarios plotted up on here for 2 different transmissivities for the Glen Rose. And kind of the key takeaways though here are that when their transmissivity is high in the Glen Rose, it's possible that there's a significant impact on drawdown. But for what we see most commonly in the Glen Rose, there's not going to be a huge impact, but there'll be a little bit. The other thing that was interesting is that when there's a lot of water moving horizontally through the Glen Rose, which is indicated by a higher T, the KV parameter becomes sensitive. So it just means there's a little bit more water available to actually leak down into the aquifer and create a different drawdown. So in short, the recharge has a limited effect, but not much. And we tested sensitivity for quite a few parameters, and that's what those results look like. So the final thing that I did was take a look at the sensitivity analysis for the 2-layer model and the single-layer model and compared them. And so what we see, if you just do a quick visual inspection, is that there's about a little less than 20 feet of drawdown or more in the single-layer model. So there's overall a little effect from recharge from the Glen Rose Formation, so it matters. The other thing I kind of looked at is there's a little bit more of an effect of recharge when there's fewer wells, and that effect sort of diminishes as you increase the number of wells. So when you start pulling out a lot of water, the amount of recharge that comes in doesn't really have has less of an impact on drawdown than it would if you were pulling out less. So this was insightful. We got to learn about how many wells you need before you need to start really considering how you're going to lay them out. And so some final key takeaways is that, just to reiterate, that in this area, the Trinity Aquifer in the study area has a low transmissivity and low available drawdown, and the way you organize new developments and well spacing is super critical in this area because there's so little available drawdown. So any opportunity to take to organize that as best as possible is going to be helpful. And there might be some limited effect of recharge from the Glen Rose Formation.